Hello, welcome back to AE 2220 Dynamics. In this video, we're going to go over motion relative to a translating reference frame, and we're going to also do an example. So we previously have considered motion with respect to a single fixed reference frame, but sometimes it's more useful to use multiple reference frames, one that is fixed and then other frames that are moving. One example where this could be the case is the cart that is moving horizontally with a pendulum that is rotating connected to it. That's a case where you could use a fixed reference frame on ground, and then where the pendulum connects to the cart, you could attach a rotating reference frame there. So when we decide that a reference frame is fixed, then all other reference frames that are not rigidly attached to that frame are moving as a result of that. Once we fix a particular reference frame, all other ones are therefore moving as a consequence. If there are two reference frames that are rigidly attached, like for example, if you have different grounded objects, and you put one reference frame there and another reference frame at the other point on the ground, then those are not going to be moving, but they're related through geometry or just scalar dimensions. The choice of your fixed reference frame is arbitrary, so that means you can fix any frame. And oftentimes there will be cases where you want to choose a particular reference frame to be fixed, and this will simplify your analysis. This is something that you'll learn as you start to solve problems and start to work with these kinds of things. Okay, we're going to consider here two particles that are moving in space. We have particle A and particle B, and we've drawn the origin, and we have a fixed reference frame shown here. From our reference frame, from the origin, we're going to draw our position vectors. Well, actually, first, we're going to start by attaching a moving reference frame to particle A. And we'll call this y prime. Let me align these. X prime and Z prime. Okay, now let's do our position vectors. So we have first our A, position vector from the origin to A, and our B, position vector from origin to our A or our B, and then we can draw the relative position vector. Let me try that again. Relative position vector, and we'll call this R, B slash A. And so here R, B slash A defines the position of B relative to the moving frame that we've attached to A here. Clearly then, RB is going to be equal to RA plus the relative position vector RB slash A. And that's how we can, again, define how two particles, their positions are related. If we go ahead and we differentiate this, and this is where things are going to change, if we differentiate, we're going to get that RB dot is equal to RA dot plus RB slash A dot, and this will then be equal to, using V's, we can have VB is equal to VA plus VB slash A. Okay. If we go ahead and we differentiate again, we're then going to find that RB double dot here is equal to RA double dot plus RB slash A double dot. Or using A's, we'll get the acceleration AB is equal to A plus A B slash A. B relative to A. And so the motion of B with respect to the fixed reference frame is called the absolute motion of B. whereas the relative motion is the one we use with that moving reference frame. Now, we haven't exactly written out what our b/a are here, our dot b/a or our double dot b/a are, and that's because they depend on the reference system that we use, or the frame of reference, and the motion itself. But we can see here that the absolute position or absolute motion of B can be defined in terms of the absolute motion of A plus the relative motion of B with respect to A. Okay, we're now going to go and look at an example shown here. A car is launched from a ramp at an angle of theta equals 30 degrees and must clear a gap of 40 feet to land safely on a ramp identical to the launch ramp. Determine the minimum initial velocity for the car to land safely. So what I'd like you to do is go ahead and pause the video and try this example. Use the algorithm approach where you choose coordinates, a coordinate system, you then compute position vectors, and then you go and compute the motion, combining all the different things that we dealt with in the past. Pause the video and give that a shot. Okay, welcome back. In this case, I'm going to go ahead and I'm going to solve the example problem using the approach that we found here. We're going to start by, first thing we're going to do is we're going to define a coordinate system. So the first step we'll do. To that end, we're going to pick an origin. I'm going to pick the origin to be the bottom of the ramp. And then I'm going to choose perpendicular directions. In this case, we only need 2, and I'm going to use Cartesian coordinates. We're going to put I in the horizontal direction, J in the vertical direction. And then we're going to have rotation counterclockwise be positive. The second step then is to define or to determine the position vectors. Define the position vectors, we'll say, for all bodies. In this case, we only have one body that's moving. We could define position vectors for the 2 ramps. However, they are not actually moving. So from our origin, and let's just label this the origin, from our origin to the cart, and we're treating this cart here as a particle, we'll have our position vector RC, and then let's not forget that gravity is included in this. So let's add gravity there, and it's launched off at an angle of 30 degrees, and we want to determine the minimum velocity of this system that's needed, the minimum initial velocity for the car to land safely. Okay, so let's go ahead and we're going to define coordinates. You can draw a relative frame here. I need to move gravity out of the way. Put it over there. We're going to put X in this direction, Y in this direction. So I've gone ahead and I've created a reference frame that is now moving with the cart, X and Y. So we're going to use coordinates X of t and Y of t to describe the motion of the system. So we'll just come in here and put a little bullet here. We might need to go a little bit lower. We're going to use coordinates X of t and Y of t to describe the motion of the cart. Or is it a car or a cart? It's a car. To describe the motion of the car. Okay. Let's actually go and move our coordinate system so that it connects to, well, actually we'll leave it where it is. It's the center of the car, and we're treating it as a particle, so all of that should be fine. We're going to start to add in some dimensions here so that we can write out what the position vector is. So we know that first RC is going to be equal to, it's a vector, we're going to have a component in the I direction, a component in the J direction as well. But we need to find where is our reference frame with respect to this system at the start of this motion. So first we're going to add in here a dimension. We'll say that this is a distance of, we'll just use a, scalar value a, and that this dimension here, we'll call this b, and then between the two carts, we'll call this h. And that being said, we need to move our reference frame to the edge here. X and Y, and then let me redefine A here. A is going to stretch to the edge of the cart, edge of the ramp. Okay, perfect. And now we need to know and determine what is our initial velocity, v0, our initial speed in each direction, in order for us to this car to make this jump. Okay, so now that we've added these dimensions, we can now determine what the position of the cart is. And in fact, let me go and redraw this position vector, because we want to take it to the edge of the car. Again, we're treating this as a particle, so we ignore the fact that the car has size to it. Okay, so in the I direction, the position vector is going to be the distance a plus any motion in the x direction. So we'll write this as x plus a. That's our coordinate x at t. That's a function of time. In fact, let's just write x at t here, just to be careful, plus a. That's in our I direction. And in the y and the j direction, we are going to go up distance b and then plus any motion y of t. So we'll say y of t plus b, all of that in the j direction. We now need to find x of t and y of t. Okay, that's what we're going to end up having to find. So our third step, after we computed these acceleration vector, or after you compute the position vector, we're going to now compute velocity and acceleration vectors. We're simply going to take derivatives with respect to time here. In fact, let's go and add time here. We're going to drop the function notation here. We're going to get x dot in the I direction plus y dot in the j direction. And then for the acceleration vector, we're going to get x double dot in the I direction plus y double dot in the j direction. Okay, so something that we know is that once the car leaves the ramp, it is going to be in free fall. It will have motion in both the I and j directions, but it's going to be uniformly accelerate downwards in free fall. So we'll add a little bullet here, and we will say that car is in free fall after leaving the ramp. What that tells us then is that the acceleration vector is going to be equal to 0I minus g in the j direction, and g here is the acceleration due to gravity. And so thus, what we find is that RC double dot is equal to 0I minus gj, such that x dot is a constant. So if we can write out the velocity based on what we've done previously, we'll write this out as v, or rc dot will be equal to some initial velocity in the x direction, or I in the I direction times I, plus that initial velocity for the y vertical direction minus g times t. And we get that by doing the integral previously. Okay. What we now need to do is consider the motion of the cart, or motion of the car. So when it leaves the ramp, it's moving with a velocity of v at an angle of 30 degrees. So first, let's go ahead and draw our directions I and j. And then for the velocity, we're going to use pink here. That's our v0 at an angle of theta. We're going to go and break this up into components. In the vertical direction, we're going to have v0 times the sine of theta. And in the I direction, we're going to have v0 times the cosine of theta, such that this v0x, this will be equal to v0 cosine theta, and v0y is equal to v0 sine theta. Okay. So that means that our velocity is going to be equal to v0 times the cosine of theta in the I direction plus the quantity v0 sine theta minus gt in the j direction. Again, equal to rc dot. And this tells us then that x dot is equal to v0 cosine theta, and y dot is equal to v0 sine theta minus gt. Okay, from there we are able to then go and integrate x dot and y dot to find, well, x and y. So x is going to be equal to v0 cosine theta times t, and y is going to be equal to minus 1/2 gt squared plus v0 sine theta times t, and in this case we're going to let the constants be 0, because the initial starting position of x and y are located at 0 for this reference frame. And the relative position with respect to origin comes from the a and b, which we're going to add in our position vector. Okay, so to repeat that, x and y are positions with respect to the reference frame at the top of the ramp. So they're the relative position with respect to the origin, meaning that they always are starting with an initial condition of 0. That tells us then that RC is going to be equal to quantity v0 cosine theta, that multiplied by t, plus a, and all of that multiplied by I, plus minus 1/2 gt squared plus v0 sine theta t plus b in the j direction. And again, that's our x. And this quantity here is our y. Okay, so in order for the car to land safely, it must travel the distance h horizontally. So we'll add that in here. To land safely, the car must travel a distance of h horizontally. Okay, so what that tells us then is that the I component of the position vector must be equal to h at the time of landing. So we'll get that v0 times the cosine of theta times t sub l, that is the time that we land, plus a, must be equal to the total distance traveled from the origin, a plus h. A plus h. Such that v0 times the cosine of theta must be equal to the h over TL. So we eliminate the a from both sides, and then we divide by TL. Therefore, we find that v0 is equal to h divided by TL times the cosine of theta. Fantastic. But we don't know what TL is, and we now need to find what that is. So let's write here that we need to find TL, and we're going to use the J component to do that. Or y of t. Okay, so the car is going to land safely when the position vector is equal to hi plus bj, h plus a, I should say. Lands safely when RC is equal to, and this should actually be RC of TL, because it's at a specific time, is equal to h plus a in the I direction from the origin plus bj. We're now going to use that y component or the whole j component, I should say. In fact, actually, we're going to use the j component. We're not going to be using y of t because we need that extra b in there. So we'll get then that minus 1/2 gt sub l squared plus v0 times the sine of theta times t sub l plus b must be equal to b, or in other words, minus 1/2 g times TL squared plus v0 sine of theta multiplied by TL. That must be equal to 0. From here, what we'll find is that we can pull out a TL, and we'll get quantity v0 sine theta minus 1/2 g times TL times TL is equal to 0. So we get two choices here. We're not just going to eliminate, you should never just eliminate a TL or a quantity in this case, because we're going to get two solutions from this. We get two valid solutions. So first, either TL is equal to 0, and that's a valid solution. And so if you eliminate TL, you will miss this valid solution. Or we'll get that v0 times the sine of theta minus 1/2 GTL, that must be equal to 0. So keep in mind that this is a valid solution. This TL equals 0 is a valid solution, but clearly not the one that we need because it corresponds to the starting point of where we analyze this. So it's the valid solution, but not the one that we need. So we're going to go with the other solution. We're going to use the other one. So we have V0 times the sine of theta, and we can bring the 1/2 GTL on the other side, equals 1/2 GTL. From there, we can divide by 1/2 and G, and we'll find that TL is equal to 2V0 times the sine of theta divided by G. Okay, let's go back and we're going to write down what V0 was. So V0 is equal to H over TL times the cosine of theta. And we're now going to plug in for TL. So we're going to get H times G divided by 2V0 sine theta cosine theta. Okay, now we have V0 is equal to a quantity with a V0 in it. So we're going to multiply both sides by V0, and we get V0 squared is now equal to, and if Hg divided by 2 sine theta cosine theta. We'll take square root of that, and we'll get that V0 must be equal to plus or minus the square root of Hg divided by 2 sine theta cosine theta. Okay, so that is our velocity. That is, we've now found and solved the problem symbolically, and then we'll plug in values to find it numerically. And what you get is that V0 is equal to, now of course the negative velocity, or negative V0 in this case, means the car is moving backwards, so we only want to take the positive value. So V0 is going to be equal to the square root of Hg divided by 2 sine theta cosine theta. And if you go and you plug in the numbers, you'll find that V0 must be equal to 38.44 feet per second. Or you can convert this to 26.2 miles per hour. Okay, and that is the end of this video. In the next one, we'll start working on non-rectangular components.